Greetings. This video is a follow-up to the first video that you viewed about z-scores. In it, we cover z-score transformations. Let's start with a table of z-scores. Before I get going, I should mention that I've rounded all the calculations so that if you try to duplicate what I've done, you're going to get a slightly different answer. Okay, so based on the previous video, you should understand how to interpret z-scores. For this table of raw scores, a score of 40 is a little more than 1.5 standard deviations below the means. This is indicated right here by a z-score of negative 1.57. Remember that the standard deviation of any distribution of z-scores is always going to be equal to 1. Similarly, a score of 48 is about 1/2 standard deviation above the mean. Okay, what we're going to talk about now in this lecture is how to compute a raw score given a z-score and a mean, or the mean of the distribution and the standard deviation of that distribution. In other words, we're going to talk about how to work backwards. So here's the z-score equation once again, and with a little bit of algebra, we can transform it so that instead of calculating z, we can use z to calculate x, which in this case I'll call x prime. Okay, so let's take a look at an example to show you how this works. We have 4 as our standard deviation and 1.84 for our z-score, or that's the one we'll work with. We do this multiplication and get 7.36, and then we add the mean, 46, to get 53. That equal sign with a squiggle on top indicates approximately equal. Approximately, in this case, due to rounding. Okay, so how do we use this? Well, the thing is that most people who haven't taken statistics may find these z-scores confusing. We have negative values, which can be intimidating. We have decimals, which can feel messy. And the small differences in the z-scores can hide the real differences between the scores. Well, fortunately, z-scores have this property that lets us transform them into something much easier to understand. Remember that each z-score tells us how far a score is from the mean, and therefore the relative distance of each score from every other score. In the last video, I mentioned that the mean of a z-distribution is always equal to 0. That makes sense because the mean represents the balance point of a data set. The sum of the values below the mean has to equal the sum of the values above the mean. Just as important, the standard deviation of z-scores, or distribution of z-scores, is always equal to 1. This is by definition, since a z-score is simply the difference between a score and the mean expressed in units of standard deviation. Okay, so because of this property, it doesn't really matter what the original mean or standard deviations were. Once we know the z-scores, we know the relative distance of each score from the mean, and therefore from every other score. So let's say that we want to report a mean of 100 and a standard deviation, say, of 10. Because the z-score provides all the information about the position of each score relative to the mean, and therefore relative to all the other scores, we can substitute whatever mean or standard deviation suits us. We can use the equation for x prime before and convert and make a conversion. So suppose that we want to report scores with a mean of 100 and a standard deviation, say, of 10. All we have to do is use this formula, substituting 100 for x bar and 10 for s. Here, the entire table with the mean is set to 100 and the standard deviation set to 10. Okay, so let's take a closer look just to acknowledge what we're seeing. Take a look at these two original raw scores, 45 and 49. They differ by 4 units. Since the standard deviation is 4, we can say that they differ by 1 unit of standard deviation. Now look at the x prime column. We set it up so that the new data set would have a standard deviation of 10, and indeed these two values also differ by 1 unit of standard deviation, since the standard deviation was set at 10. Many of the scores that you'll be working with in your careers, whether you become clinical psychologists or early childhood teachers, will use these kinds of transformed scores. So it's important to understand how they're derived and what they mean. Again, because the z-score contains all the information that we need about the relative distance of any score from the mean, and the fact, which is again axiomatic by definition, that the standard deviation of a set of z-scores is equal to 1, we can use that and then convert to any mean and any standard deviation that gives us the best expression of the data set that we're looking at. Okay, I hope that you found this useful.